this was an amazing discovery because it was a smaller planet. It's in the right kind of location to what we might be interested in for looking at other rocky planets. And water vapor tells us that water is out there. It's quite common.
Is it actually quite common then in its multiple different forms?
It does seem to be. Who knows whether there'll actually be a planet out there that could support it on the surface, but in terms of an ingredient, it does seem to be fairly common. If you don't have a further out giant planet, it could be possible that it's difficult to get the water through to the terrestrial planets.
Right, okay.
And we won't really know that until we can see compositions, but that is one possibility.
Hello, on the episode today of the podcast, we are talking to Elizabeth Tasker. She is an astrophysicist and an expert in exoplanets. If you find it valuable or interesting, please like, subscribe, leave a comment, ask a question, because it really supports the podcast. Thank you so much, Elizabeth, for joining me on Earth Ideas today. I think this is a particular topic that I'm interested in because essentially for centuries, humans knew certainly of the existence of planets in our solar system, right? The ones that we can see, the ones like, and I think people were pretty sure that there was probably other planets in the vast space that is the universe. But it's really only in my lifetime where we've been able to prove that, and then it's been thousands, right, have now been sort of registered down, and the sort of the study of it has grown hugely, and that's really exciting to me. So I suppose maybe we could start with sort of defining what exactly it is that we're talking about here. So an exoplanet is any planet in the entire universe, but not the ones in our solar system. Is that right?
Exactly. So literally from the language extrasolar planet. So it means that it's a planet that is not going round the solar or sun.
Right. And when did you sort of decide like this is something that really interests me? Why planets outside of our solar system?
I mean, I was interested in planets for quite a long time. I mean, they're just exciting, right? The idea you've got something that you sort of connect to because we're on a planet. But when I did my PhD, at the time, there wasn't a whole lot of planet formation being done in the UK. I mean, as you've just said, this is a very new field. So although I'm not so old that we had discovered the extrasolar planets by the time I did my PhD, but we hadn't got all that many. So there wasn't a great deal of research in that area. And I was really interested in computer modelling. And at the time, the UK was really very well known for computer modelling of galaxies. And I sort of asked some questions, said I'm interested in planets, but I want to do computer modelling. And another researcher gave me a piece of advice, and he said, Elizabeth, it's just scale. You know, you've got a galaxy, you've got a disk, and when you have a new star, you have a disk and planets form in that. Just change the scale bar, it'll be fine. So
just think bigger,
on that
Elizabeth.
Basis, just change your units. It will just be the same. So while I don't entirely still hold to that, I did nevertheless do my PhD in galaxy formation, and it was great. I had a really good time. But then in academia, you're on what is sometimes affectionately called the rat race, which basically means you have to keep publishing because you're on short-term contracts. You've got to prove that you're doing a good job to be hired for the next one. So it's hard to switch fields at that point. You know, you need to keep the sort of power going through the papers. So I stayed with galaxy and star formation and didn't do planets, even though it was sort of ramping up as a field, really until I became a professor, and then I had a bit more breathing space. So around that time, I was sort of thinking, oh, you know, I really am still very interested in planets. This is a fascinating field. I'd like to get into it. But how do you really find the time to switch fields? And the answer to that is you need another deadline that really helps you. And that happened when I was contacted by Bloomsbury Book Publishers. And they said, we've noticed you write a blog and we quite like it. How about you write a whole book? I mean, it's the same idea, just longer.
Again, just think bigger, Elizabeth.
Just think bigger. And again, I would say that was not an entirely accurate statement. But they said, do you want to write about galaxies? And I was like, no, I'm so done with galaxies. I want to write about planets. And they said, fine, you do that. So as I was writing the book, of course, I then had to put aside time to really get up to date with the field and read all the research papers. And so by the time I'd finished the book, which was a few years later, I'd also sort of filled in my background for planet formation, and I could start really working in the field as a researcher.
Oh, that is so cool. You made it happen and got on a really amazing book out of it, I have to say. Like, one of the sort of... in the description, we'll have all of the details of the Planet Factory, because it's really quite like a good tour of what we sort of know and what we're looking for right now, right? I mean, when it comes to other planets, we just kind of think there are a certain number of ways that they can be, and we've based that on the ones that we've traditionally known, right? And when you were sort of getting into this field and doing your research, what did you change the way that you thought much about how a planet could be? Like, was there things that you were like, oh, okay, we've only scratched the surface of what could kind of be a planet?
Definitely. In terms of the field itself, it sort of started off with surprises. It's been very unlikely we've seen something we'd be like, wow, we knew that was there. We never knew it was there.
Right.
So
right.
Perhaps one of the most famous example is just the first few planets we've discovered. So the first planet that everyone remembers, which is not actually the first planet, I'll come back to that, is the one that, of course, the Nobel Prize was awarded for just in 1999. And that was 51 Pegasi b. And this was a Jupiter-sized planet. And you might think, well, we've got a Jupiter, they've got a Jupiter, it's all the same, isn't it? Yeah. But this Jupiter has an orbit that is a year that takes just 4 days, whereas our Jupiter takes 12 years. And Mercury, our innermost planet, still takes 88 days. So 4 days is ridiculous. I mean, seriously.
Yeah, you'd get nothing done.
No, I mean, yeah. Think how old you'd be on that planet. And this was amazing because our theory of planet formation actually said this couldn't happen. You need a lot of material to build a planet the size of Jupiter. Mm-hmm. And there just shouldn't be that much material that close to the star. It should have just been vaporized. Mm-hmm. So how do you build, an absolutely monstrous planet so incredibly close to the star? Mm. And the conclusion was that you don't, and you can't. And actually, we were probably okay with our theory of building those planets in much colder areas where you've got a lot more building material. Right. But then once they've formed, they can actually change orbits. And this is known as migration. Oh, and the idea actually wasn't new. It had been proposed in the 1980s, where people had done these theoretical calculations and said, when the planet is new and it's still embedded in this natal disk of dust and gas that it formed from, that gas can drag the planet and pull it inwards. But then they looked at our solar system and didn't see a lot of evidence for this. Mm-hmm. So it was concluded maybe it wasn't important, maybe the planets formed late enough, that disk is almost dispersed, or maybe some other force just stops this happening. But then we discovered what were, imaginatively named hot Jupiters, because the Jupiters and they're hot. So we realised that actually in many systems this migration idea is a huge architect of planetary systems. Right. So that was straight away very surprising. Now if you go back to what actually was the first planet, it was discovered a few years earlier. And interestingly, it was first reported not in a journal paper, but in a newspaper, which had got a scoop. Normally you publish in the journal paper first and then you go for the newspaper. Yeah. But in this case, the newspaper got a scoop and they discovered it was happening. Oh, wow. And so they leaked it effectively. But interestingly, it was in a British newspaper that I think no longer has a paper version. It's The Independent. I think it's only online now. Is that right?
I'm not sure, but yeah.
When I was a child, we used to take The Independent and it used to sit on our kitchen table every day. And I do not remember this happening, even though I would have been just before my teens. I think this was 1992.
So it didn't make front page news? It
didn't make front page news. It's just like first planet outside our solar system.
Okay. This is, I think, what I mean. Like, people just kind of assumed, right? I'm not, like, we needed this solid evidence, but it was pretty agreed.
Nowadays, planets keep hitting the front page. So I think, there should have been enough interest. But maybe one of the reasons in this case is the planet was very bizarre. instead of orbiting a star like our sun, it orbited a dead star called a pulsar. So our star will never become a pulsar. It will become what's called a white dwarf. But if it was more massive, then when it finally can't burn hydrogen anymore, it would explode in a supernova. And what you'll get left behind is an incredibly dense remnant, which is actually made predominantly of neutrons. And if this type of star rotates very fast, then we find that jets will swing past the Earth. It has to be orientated in the right direction. Okay. But if you imagine an incredibly dense object, we're talking something the mass of the sun compressed into the size of a city. That dense.
Oh my gosh.
And it's got jets coming out of it. If that's orientated towards the Earth, you get a lighthouse effect. And as the star spins, you see flash, flash,
okay,
flash.
And that's how we see them. That's how we detect them.
And yeah,
okay,
that's how we detect that particular type of dead star. And because of the flashes, they're called a pulsar.
Okay.
And we found ultimately three planets orbiting this pulsar. But it was so completely alien compared to anything we were sort of thinking, with a normal burning star and some rocky planets.
Right.
Having this dead star orbited by planets, I mean, it's hard even to know where to put that in your picture of the universe. So I think that might be partly why it didn't make really big news, because everyone was just like, what the hell is that?
Is this even, can we even say we found another solar system? I mean, that was really one, like, the things I wanted to get into was, with you was just, are we finding that stars generally and solar systems and orbits are all kind of similar, but obviously not at all? I mean, the first two big ones that we've noted down are very, very different. Is migration a common thing then around other stars?
So it does seem to be, but there is something you have to remember. At the moment, if you just looked at our data, you would say our solar system is super different. It doesn't really match most of the other systems we're seeing, which tend to have stars very close to their stars, I mean that too, but also planets very close to their stars.
Wow.
But one of the things that's really worth remembering is that when a planet is close to the star, it's easier to detect.
Okay.
So we have what we call a selection effect, where we're bound to see those systems which have close-in planets first, because it's much easier to spot the planet in those systems.
I see.
So, for example, as I mentioned, Jupiter is on a 12-year orbit. Now, if you were looking at what we call a transit system, where the planet passes in front of the star and you see a small drop in starlight due to that planet, that's one way to detect planets. But if you want to detect a planet, you really need 2 or 3 transits to be like, okay, that's a planet.
Yeah.
So for Jupiter, that's going to take you 12 times 3 years.
Yeah.
And we haven't been looking for planets that long.
Yeah.
So therefore, it's much harder to find planets that are further out.
Right, right. And would something as small as, say, our little Pluto, like, would that make a shadow in front of its star even? Would we be even able to detect it at the moment?
So I believe, at the moment, probably not. I think a bigger problem as well is that the transit requires a very exact alignment. It's got to be you on Earth, the star, and then the planet in between you. You've got to be along that line of sight. And as you go further from the star, any slight angle will mean you're no longer on the line of sight. So if you're close to the star, you've got a better chance of transiting than if you're further away. So Pluto, which is already really itty-bitty, is also really far away and also on an inclined orbit. So the chances of seeing it are, it's not really going to happen.
Yeah.
Even if you were sensitive enough to detect its dip in starlight.
Yeah. So as well as a sort of selection bias on the types of planets that we're able to see, which, sounds like a tiny percentage, are we also, what we're able to know about those planets, is it mostly just about their orbits then?
At the moment it is. I personally feel this is a particularly exciting time for planet formation, though to be fair you could probably ask me about, I give the same answer any time in the last 30 years, but this time I'm telling you it's an exciting moment.
Okay.
So at the moment I feel we're on a brink. Like everything that's gone before has been about detecting these planets. So things like the Kepler Space Telescope and indeed the successor that's flying currently, TESS, these have been about identifying these worlds, finding out, are they even out there? Is planet formation common? And the information these spacecraft get is very limited. It gets, yes, positive detection of the planet. it gets either the planet's size or its minimum mass. Sometimes if you manage to detect through multiple telescopes, you get both. And it gets its orbit, which tells us how much starlight it receives. But that's it. We don't know anything about surface conditions. We don't know whether it has water. We don't know the composition. All the things that would tell us, is this truly an Earth-like planet? Or even, in some cases, is this truly a gas giant like our gas giants? Without being able to tell the composition, we can't really have that information. So we're edging now towards the next generation of instruments, and they are going to be aimed at what we call planet characterization. So not looking for new planets specifically, but following up planets we already know are there and trying to discover actually something more about them, which usually means doing what we call transit spectroscopy.
Ooh, okay.
So if you imagine that planet passing in front of its star, most of that light, well, most of the light isn't affected at all, but a chunk of the light is affected by the planet, so you get the dip. But a very small amount of that light is going to pass through the atmosphere.
Okay.
So that light will depend on the wavelength, because different molecules in the planet's atmosphere will absorb different wavelengths of light.
Right.
So if you look at that same transit in multiple different wavelengths, which would be the spectroscopy part of transit spectroscopy, you'll see it changes size very slightly, sometimes opaque, because at that wavelength the molecules are absorbing very strongly, and sometimes it will appear very slightly smaller because there's no absorbing molecules at that wavelength and the light passes straight through.
Right.
And by measuring that, you get a fingerprint of the different molecules that may be in the planet's atmosphere.
Wow.
And that gives you your first indication of what actually might be going on inside the planet. So it moves from being a shadow, where we just see, the size, through to seeing the product of the system of the planet, its chemistry, biology, and even biology.
Wow. So instead of just knowing, okay, there's something going across here, we're starting to be able to see, we're seeing something and we think it might be made up of these certain things.
Exactly.
How many planets have we dived into? I say we. It's not me at all.
Me. I can say I personally observed. No, I'm actually a theorist. I haven't personally observed anything. Sorry, collaborators, if you're listening to this.
But the human race gets all the credit every time we do anything out in space.
Absolutely. So definitely a we.
So I support this.
I'm actually not sure of numbers, but mostly it's the large planets currently, the gas giants. So obviously, because they're big, they're easier to see, and therefore it's easier to do this transit spectroscopy. We've tried for a few sort of rocky planets. Indeed, there's a planet that is sort of in between, maybe rocky, maybe gaseous, that hit the news quite recently, K218b. It's about a year ago. I remember this because at the time I was in the UK, and of course I haven't been back since thanks to the pandemic, so that's how I know roughly when this discovery happened.
Pre-coronavirus.
But I think, yeah, exactly, when planes were still a thing. And it's exciting discovery because they discovered evidence of water vapour in the atmosphere.
Wow.
And this planet is actually also in what we call the so-called habitable zone, meaning that it receives similar levels of sunlight to the Earth. But in fact, the planet's quite a lot larger than Earth, so whether it's even a rocky world we're not clear. It might be sort of in between a Neptune and an Earth, where you probably have a rocky surface somewhere, but then you have a very thick atmosphere that might have a lot of hydrogen in it. And hydrogen, like carbon dioxide, is another greenhouse gas. So the right level of sunlight for the Earth will be far too much for a planet with hydrogen in its atmosphere to have liquid water.
Right.
So therefore the water vapour is most likely vapour. It's not actually liquid. But nevertheless, this was an amazing discovery because it was a smaller planet. It's in the right kind of location to what we might be interested in for looking at other rocky planets. And water vapour tells us that, water is out there. It's quite common.
Right.
So that was an exciting discovery.
Is it actually quite common then in its multiple different forms? Are we finding
it? Does seem to be. We've seen it also, in addition to planet atmospheres, we've also seen it in the protoplanetary disks that make the planet. These disks of dust and gas that circle the young stars. We've also seen evidence for water vapour in that too. So, it's who knows whether there'll actually be a planet out there that could support it on the surface, but in terms of an ingredient, it does seem to be fairly common.
Oh, that's very exciting. So the theory is that how water got to Earth is by arriving on an icy asteroid, right? Is that, with other planets, do you think that is a likely way that water could arrive? Or...
So I would say, first of all, it's not absolutely definite that's how we got our water.
Okay.
But it is one of the main theories. And indeed, the Japanese mission and indeed the NASA mission, Hayabusa 2 and OSIRIS-REx, are currently collecting and bringing back samples to Earth that will look very closely at one of these asteroids that might have been the type that hit Earth and brought our water.
Ooh.
So Hayabusa 2 is due to arrive back with its asteroid sample on December 6th. So really close now.
That's the day before my birthday. That's
really?
Amazing.
Well, you're getting the best birthday present ever. So that's very exciting. But yes, you're right. It's one of the main theories. And it's an interesting question whether other planets would definitely have the same mechanism. So, for example, one of the reasons we think this is necessary is that at our Earth's position, water shouldn't have been able to form ice. It's just too warm at our orbit.
Right.
So that means that when you're building a planet, how do you encapsulate the water in the planet? Mm-hmm. There are a few different mechanisms, but the easiest would be if it was solid ice, so that it just joins in with the building process.
Just
and voila, you've got water. Yeah, boom, there. Which is how the icy moons like Europa and Enceladus could quite easily accumulate water. They did form where water could be ice, so very easy just to collect it all together. Mm-hmm. Now, if you need a delivery mechanism, so if you assume, okay, well, any planet that forms in a sort of Earth-like location will have this same problem, and therefore it also needs a delivery mechanism, you have to start looking at the whole system of planets. In particular, Jupiter is a bit of a bully. So it's this huge gravitational force in the solar system. And there's actually a series of research papers written by a researcher called John T. Horner, who asks Jupiter, friend or foe? Like, is Jupiter helping us by stopping, asteroids destroying the Earth and maybe also scattering water-rich asteroids in our direction? Or is it actually a foe and it causes most of those asteroids to come in our direction? Like, what's the gravity doing? Is it acting as a block or is it acting as a scattering agent? Now, if it's needed to scatter rocks inwards towards the sun, so basically you've got this big gravitational force, you've got these icy asteroids forming around Jupiter. Mm-hmm. They're drawn in towards Jupiter's gravity, but then they overshoot.
Right.
Because they've started to move very fast because Jupiter's pulling very hard, and they overshoot the planet and they go towards the sun, and then they hit the terrestrial worlds. So if you need that, what do you do if you don't have a Jupiter? So if you don't have a further out giant planet, it could be possible that it's difficult to get the water through to the terrestrial planets.
Right, okay.
And we won't really know that until we can see compositions, but that is one possibility.
So once we sort of are able to see whether these smaller terrestrial planets in solar systems without a Jupiter-sized planet actually have water, then we'll be like, okay, well, there's another way then that water is getting there. Oh, this is very exciting. So our solar system is rare in the way it seems, as we were talking about earlier, with quite spaced out planets far away from a sun, right? Is it?
Well, we don't know because we can't see the equivalent planets. So based on our current data, yes, it's rare. But always have at the back of your mind it could be completely common, but we can't see the others yet.
Yep. Okay. Are we? So is Jupiter? Is that kind of like the biggest that a planet will get? Is that quite a sizable planet?
No.
Oh.
I mean, yes, it is sizable. I will definitely. I agree that Jupiter is a big planet. Completely happy to put my name on that statement. But it is not. It is not the biggest we found. I'm not exactly sure what the biggest we found is, but you certainly get sort of supersized Jupiter planets. Interestingly, there comes another question when you start looking at very large planets. When is a planet not a planet and actually a star? So you go to Jupiter sized and it's already pretty meaty but a lot smaller than our sun. On the other hand, there are stars that are a lot smaller than our sun too, called red dwarfs. So where's that cutoff between a planet and a star, and how do you define it? And there's no answer to that. I can't actually tell you. All I can tell you is people try to sort of do this cut-off. In particular, once you start having something that is about 14 or so Jupiter masses, so quite a lot bigger than our Jupiter, but still smaller than our sun, it can start to burn not hydrogen but deuterium, which is a heavier isotope. So hydrogen has 1 electron and 1 neutron. One electron and 1 proton. Thank you. Whereas deuterium has that 1 electron, 1 proton, and 1 neutron. So chemically, it's very similar, but it's a bit more massive.
Right.
And at 14 Jupiter masses, you can start to fuse deuterium. And we call that a brown dwarf. So it's not quite a star yet, but it's definitely not really a planet. So one sort of divide people put in there is a sort of brown dwarf divide, and they start to say around 14 Jupiter masses.
Right.
Another way that I would like, but is much harder to do, is to say, look, if it forms in a disk around a star, it's a planet. And if it forms in its own little cocoon of gas, then it's a star. But you would have to know how something formed. And of course, we tend to see them quite late on in their evolution. So you haven't got much evidence of how they formed in the first place.
So does this suggest that there is a sort of lifespan of a planet? And that could include becoming a star at some point?
No, it would either be a star or a planet. It wouldn't evolve into one.
Okay. So
it would either start massive enough to be something starish, or it just would never get that massive.
Right. Do planets have a sort of lifespan? Do they evolve in ways, or do they sort of form and then...
Yeah, it depends kind of how you define lifespan. So, for instance, you could define it in different ways. Planets can certainly die quite dramatically. So in particular, I mentioned this ability to change your orbit during the beginning of your life. So you form that planet, you still got that disk of dust and gas around you, and you can be pulled inwards. That's actually a pretty dangerous process, because sometimes you don't stop. So you just go straight into the star. Goodbye, good night, it's all over.
Right.
Sometimes you end up on such a close orbit that the heat from the star is ripping that planet to pieces. And we've actually seen evidence of that. In very close orbiting planets, you can see the material just being dragged and evaporated away by the star.
Oh my God.
So for those on sort of dangerous orbits, that can happen. Another awful thing that can happen to you is that, you survive the gas disk, you're on a safe orbit, and you're like, well, I'm golden, I'm clean and dry. No, not necessarily. So, for instance, it's possible that if you pass close to another planet, imagine they're on 2 orbits, and while they're on different places in their orbit, everything is safe. But as you orbit around the star, just at some point, you might come quite close to each other.
Wow.
If you're big, especially, your gravitational forces may cause a scattering event. And then you can be injected entirely out of the system. So you're still a planet, but you no longer have a mother star.
Wow. It's so
and
dramatic.
You can just become a rogue world. It's very sad. I mean, it's even possible. Some simulations predict that we once had 5 gas giants, and one hopped it.
And it could just be floating out there without a solar system.
Floating out there without a solar system. We call those rogue planets or orphan worlds.
Oh, and how are we detecting those without being able to see them against a star?
So there are some ways. It's quite difficult because most of our detection technique does require the star to provide some light.
Right.
One way you can do it is through a technique called gravitational microlensing. So in that system, you get just a chance alignment with a background star. And the gravity of the planet, which you can't see, but its gravity actually causes the background starlight to bend around it, because light is actually influenced by gravity. And that bending causes the star to momentarily brighten. It's sort of the opposite of a transit. And so if you see that momentary brightening, that can indicate there is an unseen but massive object in your way. And that might be one of these rogue planets. The problem is it's a chance alignment. So you see it once and you can't repeat the observation.
Right. So again, it's just sort of guessing and thinking. Does all of this make you feel like we like, as you just said, we have to know things because of light, and that's our main sort of like sense and our way of experiencing the world? I mean, does it make you really question what we can't see because we're only seeing things?
Oh, certainly, but I would argue that's someone else's department.
Oh,
so
yeah.
in particular, I would say that's for the gravitational wave guys to work out.
Right, okay. There just must be so much out there that we have really no idea about, right?
Absolutely, definitely. But I think that's where computer simulations come in too. I mean, you need a computer simulation is obviously compared to observations to know if it's right or wrong. But if you compare to, the observations you can see with the parts of the simulation, and if they match, you might assume that the rest of the simulation, which might not be visible, is also correct. So that can give you the ability to look back in time, to look at things from different angles. And it is always guesswork. You have to take in new observations as they come, check it still aligns with that simulation. And if it doesn't, you're back to the drawing board.
Yeah.
But you can, while you're matching these two closely together, you can get a feel for what the unseen matter is doing as well.
These sort of areas, is this the new technology, the new ways we're sort of thinking about trying to detect these planets and learn more about them? What other new things that people are coming up with?
I think, these are all going to involve light, but I think one of the most exciting upcoming areas is a direct image. There's nothing really that beats a direct image in terms of what you want to see. You're looking actually at the planet. That's very exciting. And at the moment, because planets are dim, it is hard. We typically see young gas giants, so Jupiter but younger, because when they're younger they're hotter and they emit a lot of infrared heat radiation and it's easier to spot. But we're building bigger and bigger telescopes for those, particularly on the ground. So the 30-metre telescope and the European Extremely Large Telescope, we really are very good at naming things. So these instruments, and also Japan has Subaru, which does some direct imaging, these are all aimed at trying to see the planet directly. And while currently it is aimed at gas giants, we should, with the next generation, at least try to be able to observe maybe more rocky-like planets that are around smaller stars. So not around stars like our own sun, they're too bright. But if you look at M dwarfs, which are dimmer, and give you more of a fighting chance of seeing the planet, it's possible this next generation of instruments that's being built right now might be able to directly see rocky-sized planets around those M dwarf stars. And that's really exciting.
Yeah, so that is quite a lot of the field focused on trying to find Earth-like planets. We mentioned the habitable zone and the search for water, but also the size and being rocky.
Certainly astrobiologists are very keen on finding an Earth-like planet because they've got an even harder job. You're trying to detect these atmospheric signatures, what gases are in the atmosphere. But that signature is going to be a giant combination of everything the planet's doing. Its volcanoes, its internal geology, any chemistry, any physiochemistry, and then finally, if it has any biology. And this is all tangled into a signature right at the top of the atmosphere that you can detect. So it's a hugely degenerate system. And the problem is, if the planet is very unlike Earth, it might be doing a lot of abiotic things, that is, chemical reactions that do not involve biology, that we've never seen on Earth because conditions are different here. So you're going to have to find a signature that you think it might be biology, and then you're going to have to rule out any other way it could be formed. And that's immensely difficult. So the best chance we have of doing that is if the biological signature resembles Earth. And that means an Earth-like planet. So it's not that we think that life should be restricted to an Earth-like planet, or even that might be the most interesting discovery. It's just that it's our first opportunity, probably our best chance of identifying a biological signature.
It's what we know, so that's where we
we have something to compare to, which is really important. But in terms of non-astrobiology, I personally am really interested to see how different worlds could be. Like, for example, this idea of migration, that you can move planets in. Imagine if you formed a smaller planet than Jupiter, much further out from the star, so past where you can freeze water into ice. So this might have a huge amount of water. And then supposing it migrates in, so now it's close to the star and we can observe it. What would the geology on such a planet be like? Like, we think of the Earth as a really watery planet, but actually it's only our surface that's covered by water. By mass, we're less than 1% or 0.1% water. It's really tiny.
That's so true. Yes.
So, but if you formed where there was ice, you might be 50% water. That's insane. So as you move in towards the star, that water melts and you might become a water world. Now, could a water world support anything like the geology that we have on Earth? Could it have volcanoes? If it did have volcanoes, would they emit the same gases, or would they emit like ammonia and other ice-rich compounds instead? That would be really interesting to me.
Yeah, and would they have, sea creatures essentially? With the life is, began in water, we think here, right? So
it did, but there are some reasons why we're a bit skeptical. So if migration is common, it's possible we might be dealing with a lot of water worlds. So it's an important question for the astrobiologists of whether do we forget these worlds, or do we say, well, hey, let's go get them.
Right.
And NASA's astrobiology mandate is follow the water, which sounds very promising. And it's also true that on Earth, wherever there is water, we find life. Even in the most crazy places like these deep sea hydrothermal vents where you get no light. No light, not a problem. There's water, it's fine. We can do it. But if you have so much water that you're completely covering all the land, you may suppress something called the carbon silicate cycle on Earth. So the carbon silicate cycle is what changes the level of carbon dioxide in our atmosphere over geological time. So it doesn't provide really any support against global warming because it's happening much faster. But over geological time, you can add and subtract carbon dioxide from the atmosphere. And that you do it, well, the reaction works in proportion to the temperature. So, for example, when our planet was younger, the star, otherwise known as our sun was cooler. And so the Earth should have been a snowball, but we have quite a lot of evidence that it wasn't completely frozen over. And the chances are this carbon silicate cycle was able to put enough carbon dioxide into the atmosphere to give us a bit more protection, basically giving us a thicker coat. And if you don't have that cycle at all, it means that the amount of sunlight or starlight has to be absolutely perfect for the right conditions, because you've got no way of adjusting your surface temperature. And because starlight changes over time, it means that, the epoch in which you had those good temperature regions is going to be very low if you have them at all. So that might make it much harder for a planet to develop life.
Whoa, I mean, we really were the Goldilocks, right? For the life as we know it. That is so incredible. But like we were saying, we've only just started looking in the last few decades. So it's so hard to say how special Earth really is. What did you think? I read recently that a detection of some sort of molecule, I can't remember what it was, in the clouds around Venus is a clue.
The phosphine discovery.
Right, it potentially could be a sign of life living in Venus's clouds. What did you think of that?
So I absolutely love this discovery, though I have to say it's now starting to look like it may have been a false detection.
Oh no.
There's been some more research. But I still feel that this was awesome, because I think it's going to demonstrate what we're about to go through. You thought 2020 was frustrating. It's going to be nothing compared to what astrobiologists are doing over the next 25 years.
Feel sorry for the astrobiologists.
They're going to have it really rough. Okay, maybe not quite as rough as 2020, but it's going to be a very frustrating process. And I think the cycle will be very similar to the phosphine discovery. You're going to have a detection of something that on Earth would definitely mean life, and that's phosphine. So on Earth, almost all phosphine is biologically produced. Where we've discovered phosphine that's not biologically produced is not the conditions you would expect on a rocky planet like Earth or Venus. So, for example, it is produced in the gas giants, but you need a very hydrogen-rich environment and very high pressures, and neither the Earth nor Venus have those.
Right.
So that was why this idea came about. And the original Nature paper is, very careful on this. It says, look, phosphine on Earth would mean life, and we don't know of any abiotic way of producing phosphine. But that doesn't mean to say there is not an abiotic way of producing phosphine. Venus is a very different environment, and it could be that there's just chemical reactions that we haven't tried in our laboratory because they're so alien to us that are happening on Venus and could be producing this phosphine. So they were very cautious straight away, but definitely interesting. And then there was a bunch of follow-up observations, and a couple of papers have come out since then suggesting that maybe phosphine isn't there at all. And this was due to the difficulty of analysing the data, because it's a very complicated system. So it actually might not be phosphine there. And I think this same process is what we're going to see when we start being able to get data from rocky planets,
Mm-hmm.
we're going to see signatures. They're going to be immensely hard to detect. So the first problem could be that when you try to redetect them again, you don't find them. That's going to be the first problem. And the second problem is going to be that while on Earth it might mean life, on another planet it might not mean life. And I think this is going to be the process. And the scientific process does suggest that you publish the paper, because publishing a paper is really a conversation call. It's not a full stop. It doesn't say, we've made this discovery is fact. It says, we found something interesting. What do you think? That's the point of a paper.
Yeah.
So then other groups sort of leap on board. And I think in most cases they will contradict, but that's what they're there for.
Yeah, I mean, that's what's so exciting about science. There's not a single scientist. I feel like most really great scientists don't come with any kind of ego around that. They just with the discoveries, and then it's very much a collaboration. I was having a conversation with another space physicist a few weeks ago for a podcast about space weather, and we totally talked about, particularly in the space fields and in the space industry, it's because it's so expensive to do these studies and collect any data. There is this international collaboration, which is just, I feel very special, and the way that scientists and people excited about space are so collaborative is, I mean, we could learn a lot from it in many other ways. We could all take some lessons from the way that space is done.
I think that's, well, in ideal case, it's definitely true. There's obviously a few exceptions from time to time, but I think, these always should be international collaborations. They require the use of instruments that are international collaborations in of themselves, because they're so big and they're so expensive to build. And, space missions, no one really goes to space alone anymore. So, NASA, ESA, JAXA, ISRO, all these space agencies, they have international partners and collaborators. And it's right that they do, because the questions they're trying to tackle, like, how did water arrive on Earth? These are questions of humankind. They're not questions of one country. It doesn't stop at the boundaries.
We talked about potential new technologies and telescopes that we'll be installing, but what do you think is the next big project for looking at exoplanets and for understanding planets?
I think probably those instruments are going to be the big one. I mean, we've got JWST, whose launch keeps being postponed so much, it's become a bit of a joke, but it is going to be an amazing telescope, and I'd much rather they waited and got it right than launched with problems. So that's going to be not just for planets either. It's an all-purpose observatory. It's going to be amazing.
Where is that going to be?
It's going to be at L2, so it's between. It's up there somewhere, Laura. Somewhere.
It's high up.
It's in space. I don't know. It's on a higher orbit than Hubble, which should give it a particularly good view. So the problem with that is it's a more hard to reach orbit as well. So Hubble, we did a repair mission. I'm going to say we again, as if I was involved somehow. And with JWST, we can't do a repair mission. It's out of reach of humans based on current capabilities. So, let's delay that launch and make sure we get it right. But that's very exciting. There's also going to be the European Space Agency mission Ariel, and that is purely for looking at exoplanet atmospheres. It's going to be focused on planets that orbit very close to the star, because it's easiest to see them and their atmospheres. But it's going to provide the first survey of exoplanet atmospheres. So I said we've got a few so far, but not really enough to do any statistics or say anything generally about it.
Yeah.
Ariel will change that, and it will do a really quite a large survey of certainly hundreds of planets to get their atmospheric composition. So that's going to be really exciting. And then we have, complementing those, the ground-based telescopes. We've got the extra-large telescope, and we've got TMT. So they will also be coming online in the next sort of decade. So that's going to be really exciting. And they measure slightly different things. You do need both. Some people say, why don't we just send everything into space? And you can't get as big a collecting dish in space for a start, because you've got to launch it. So that's the first problem. And also, heavy equipment, things like these spectrometers that see things at lots of different wavelengths. They're much easier to build on the ground, and then you can effectively hot swap as well. You can update the instruments, whereas with a space mission, once it's up there.
Well, yeah, it's gone for
it,
years.
Yeah.
Yeah.
So you can't do any updates where you can on the ground. So you can do much bigger collection dishes. You can have much more heavy instruments because you don't have to worry about that launch anymore.
So if you had, this is a question that I usually ask people with much smaller budgets and much smaller resource needs. So I'm going to say, if you had an unlimited amount of money or resources to answer one question that none of these telescopes are addressing about exoplanets, what would you ask?
So controversially, and I will defend my decision, I would go to Venus. Now, you might say, Elizabeth, we just said exoplanets, and Venus is literally our neighbour, not the exoplanet part. And yes,
I'll let you have it, though.
You have a good point. I do acknowledge that. But I will defend this by saying that our solar system has 2 Earth-sized planets. Venus and the Earth are almost identical in size. And we don't understand why they're so horribly different. I mean, Venus is closer to the sun. It's not in what we call the habitable zone, but that alone cannot explain its extreme environment. People often talk about Venus having undergone what we call a runaway greenhouse, meaning that carbon dioxide ended up getting a lot of it into the atmosphere and then it heated up and heated up and heated up. But if that were the only difference, then you should be able to strip away Venus's atmosphere and see a very Earth-like planet underneath. And you don't. You don't see plate tectonics. You don't see a magnetic field. You see a surface that's all roughly the same age. I mean, how is that even possible? It's very mysterious, Venus. But I feel that until we can tell the difference between the 2 Earth-sized planets that we can actually visit, then in some ways we're just playing around by looking at exoplanets that are Earth-sized. Because if we can't distinguish between 2 that we can actually stand, well, we can't quite stand on the surface of Venus, but we can go down to the surface of Venus, then, how are we supposed to really know what a planet where we can only see that top layer of atmosphere is truly like in comparison?
Wow. So what are your theories? Like why it doesn't have anything going on down there? It's just like a solid rock.
That's interesting because it shouldn't be. It should have a core because it should have had similar composition to Earth. It formed right next door. So why hasn't that iron core?
Right.
And anything that's large should have what we call differentiated, where the iron sunk to the middle. And that sort of minimum size is not particularly big. I think it's only about maybe 150 kilometres. I apologise to my planetary science friends if I'm off there. But it's not huge. Like large asteroids differentiate. So this should have happened to Venus. The iron should have gone down. And there are different theories. One theory is that for various reasons, it might have what we call an internal magma ocean. So the Earth probably had a magma ocean. It was probably magma at one point, but eventually it cooled and solidified. And maybe that just never happened on Venus, and under its surface, it's still magma, which could be preventing that magnetic field forming. The other possibility is maybe our moon-forming impact played a very big role in mixing all our layers together. And without that, maybe Venus has ended up what we call stratified, with very sort of neat layers going all the way down. And apparently that's not good for a magnetic field either. So the internal structure basically could be a problem with Venus. That's one possibility. Maybe it doesn't have plate tectonics because it was that extra heat. Maybe it was just enough that the crust didn't sort of snap into plates and it was able to heal itself. But a lot of this could be answered if it was possible to put a seismometer on the surface of Venus. Because by feeling the waves going through the planet, you get a strong idea of its internal structure. But the surface of the planet can melt lead. So how do you put a seismometer on it?
So, my God. But we've landed something on Venus before.
The Russians have in particular, the Venera missions. Now, interestingly, the Venera had a whole series of missions, and it was sort of Venera 13 and 14 that actually landed, maybe one of the earlier ones. I think Venera 13 is the one we have the pictures from mainly. But the first Venera missions had no idea what we'd find beneath the clouds because we couldn't see the surface. And indeed, the early Venera mission, at least one, was designed to land on water because we thought it was possible there might have been oceans down there. We just had no idea, which tells you how far we were from the truth. That, in fact, that when that probe passed through the atmosphere before it was destroyed, it sent back enough data to tell us that the temperature and pressure meant the water was not on the cards whatsoever. No longer need to prepare for that water landing.
My God. That's amazing. I mean, this just goes to show why every time we find an Earth's-like planet, it's, it just we have no idea.
I wrote
it's ticking one
Exactly.
box of many, many,
I
many.
wrote a small app that goes on a Chrome browser, and when you see an article saying Earth-like planet, it replaces it with Venus-like, and all through the size. Because we only know size, so is that?
And this is why.
Earth is the same as Venus in terms of what we can currently see. So the little app just goes through and does Venus size, Venus size, Venus size all the way through.
Yeah.
But these missions happened in the 70s and 80s. We haven't tried to go to the surface of Venus for a very long time. So currently the only orbiter around Venus is the JAXA Akatsuki mission. And fairly recently we had the European Venus Express mission too. But I think it's time that we went back to Venus in a serious way, because I don't think we're going to understand rocky planets or planet habitability without really understanding this planet that's next door to us.
Absolutely, it's a mystery right next door. We need to know. Do we know anything about how Venus formed, or when it formed, do we just know she's there?
It should have all formed at the same time of Earth. If you do, because it has to form in that protoplanetary disk. We're pretty confident the formation time must be very similar to the Earth. You have a pretty tight boundary on that. But what happens to it afterwards is where it gets confusing. I mean, it's similar in size to the Earth. It should have formed with the same composition. There's not an obvious way to form it with a different composition. But really, until we go down there and give it a poke, it's going to be hard to find out more.
It's like a sister and a brother that sort of
yes,
split
exactly.
off and then went their own separate ways.
And I think it's really important to know why. Like, for instance, one of the conferences I went to did this thought experiment. So no calculations. We were just sitting in a room. And someone asked this question: what happens if you swap Venus and Mars position? So you move Venus into a colder area and you move Mars into the warmer area. Do you end up with 3 habitable planets or not? And the answer was, we haven't got a clue. But one of the problems was, because we don't know how Venus evolved the way it did, do we know for sure that its position is why it's not Earth-like? Like, for instance, maybe plate tectonics is just a stochastic process, like it's fairly random. So you could form the Earth again in exactly the same position, and it might not form plate tectonics. We're not sure. So if you need a moon-forming impact to make your internal layers sufficient for a magnetic field, say, maybe, again, that's stochastic. You might just not get a big enough impact again. So without knowing, like, what's random, what's position-based, where does this split happen and why? It's very hard to talk about planet diversity.
Okay, so I can't give you this money to send something to Venus, but maybe one day. But what's next for you actually then? What do the next few years look like for your research?
I work at the Japan Space Agency, so we have quite a few missions that are definitely going to be tackling the questions of how our planet became habitable, looking in particular at water flow. So we've got Hayabusa 2 coming in fast in December 6th. So that's very exciting. And then the next big mission for JAXA in terms of planetary science is a mission called MMX, Martian Moon Exploration Mission. And that's going to go to the Martian moons Phobos and Deimos. And it's going to try and collect a sample from Phobos, which is the innermost moon. And these are mysterious little beasts because we don't exactly know how they formed. They look like potatoes, which, rather than suggesting they're truly vegetables, might suggest they're asteroids that have sort of come too close to Mars and been snagged. But Mars is, excuse me for saying so, Mars is kind of pathetic. It's not very big. We always sort of see it as this giant globe that looks sort of Earth-like, but actually it's half the size and it's 1/10 of the mass. Like, it's not a big planet.
Right.
So, for it to snag 2 moons is a bit cheeky, really. We don't really think that's going to be very easy. So another possibility is, like us, it suffered a giant impact, and the 2 moons were formed as our own moon was from this debris. But both are quite interesting in terms of looking at water, because if it did snag these asteroids to become its moons, then they're revealing sort of the material that formed the rocky planets. So very early material in the solar system, and you would sort of see they must have formed further out and been drawn in. So we would see how water was sort of flowing inwards through the terrestrial system. But on the other hand, if they were carved from an ancient Mars, then they're time capsules to how Mars might have been in much earlier days, where we think it's possible there was water and maybe even a habitable environment on that planet. So that would give us evidence of what Mars might have been like at much earlier times, and therefore how a planet could in fact be born and die. in terms of habitability.
Okay, I've definitely heard about this idea that Mars may have once had water and may have once had life, and it's kind of on the other end of all of that, somewhere where Earth might end up
Quite possibly.
one day.
I mean, Mars had some disadvantages. It lost its magnetic field. It actually had one at one point, but for, again, reasons that aren't entirely clear, but may have involved a massive collision, it lost its magnetic field. And that meant its atmosphere started to be stripped away by interactions with the wind coming from the sun. So that was not helpful to habitability, I think we could safely say. Atmosphere is useful. That was one problem. For the Earth, it's also possible that we might one day lose our magnetic field. Eventually we'll lose internal heat and cool down, but that's a very, very long process. So we don't have to worry too much about that. Ultimately, it's not the problem for 2021, I think. But eventually the sun will die, also not the problem for 2021, but eventually it will die, and at that point it's not looking good for any of the planets, really.
I just to sort of make clear that our magnetic field is what protects us from the sun's, like the solar winds and the radiation.
Yeah, absolutely. So when you see the northern and southern lights, that's high energy particles that are coming from that solar wind, and they're being driven around our magnetic field, and then they interact with the gas to produce the green and blue lights of the aurora. So that's evidence of our magnetic field. And yes, without that, we would get a lot more harmful radiation on Earth.
It does sound like Earth is very, very special, and we're obviously very, very lucky to have it. But the last sort of few decades of you and your colleagues' work to search for Earth-like planets, obviously, generally humans are pretty... the gut feeling is that there's plenty of Earths and plenty of possible life out there, right?
I think the question is, if you added up everything Earth was, you would certainly have a hugely long list that seems very hard to replicate. But the question is, how many of those processes are effectively inevitable when you have a rocky planet? Like, you need an iron core, but as I've just said, we kind of expect an iron core as soon as you get larger than a few hundred kilometres. So maybe that's not rare at all, and basically everyone would have one. How common is it for that to generate a magnetic field? Well, Mercury and Mars and the Earth all have, at least at some point. It's just sort of Venus that hasn't. So maybe it's fairly common to have a magnetic field. Maybe it's not always needed. We're not sure about that either. We have a lot of geological cycles that certainly help life on Earth, but maybe there's alternatives. That's what we don't know. Maybe life could thrive perfectly well without them, or substitutes could be made.
I always want to talk to people again, and I want to find an update, but I think I may have to wait quite a few years to get to talk to you again for any sort of significant update. But thank you so much for this chat. That was very interesting, very exciting.
Oh, thank you.
Yeah.
Thank you very much too. It's been fun.
Yeah, awesome, cool.